For most of human history, if we wanted to understand our planet's water, we just looked at a map. We assumed everything there was to know about our oceans existed right here, splashing against the solid coastlines. The Pacific, Atlantic, Indian, Arctic, and Southern Oceans form a continuous blanket that covers over 70% of the globe. But far beneath those ocean floors, deeper than the tectonic plates, deeper than the lowest mine shafts humanity has ever carved out, scientists have detected something strange, a hidden reservoir of water buried hundreds of kilometers underground. To understand the true nature of Earth's water, we have to stop looking at the waves and start looking deep inside the solid rock of the planet itself. Earth formed roughly 4.5 billion years ago from a violent swirl of rocks, dust, and planetary fragments. The young planet was unimaginably hot. The surface was a churning sea of magma, and under those extreme, fiery conditions, any original water should have instantly boiled away and escaped into space. Yet look at this equation. This is the total estimated mass of Earth's surface oceans, 1.4 times 10 to the 21st power kilograms. That is an enormous amount of water for a planet that supposedly baked itself completely dry. For decades, scientists reasoned that the water must have arrived from the sky. They assumed that icy comets from the outer edges of the solar system bombarded the Earth after it cooled, delivering our oceans over millions of years. Here is where that theory runs into trouble. This chart maps the isotopic composition, the chemical fingerprint, of Earth's oceans compared to samples from various comets. The comets form a distinct cluster over here and do not perfectly match our oceans. Because comets cannot account for the entire ocean mass, a massive chunk of our water must have been here from the very beginning, somehow surviving that fiery planetary formation. To figure out how water could survive a molten planet, we have to rethink what water actually is. Chemically, it is simply H2O, 2 parts hydrogen, 1 part oxygen. Nothing requires those atoms to take the physical shape of a liquid pool. That brings us to a specific mineral called ringwoodite. It forms deep inside the Earth's mantle, in a transition zone sitting between 410 and 660 kilometers below us. Down there, extreme pressure changes the rules of chemistry. This model shows the crystal structure of ringwoodite under high pressure. At depths exceeding 20 gigapascals, 200,000 times normal atmospheric pressure, hydrogen and oxygen atoms are forced to lock directly into the solid geometry of the mineral. This is known as structural water. There is no giant, cavernous sea sloshing around in the dark. The water is completely invisible, fused permanently into the rock itself as a solid geological layer. Testing this structural water hypothesis directly is logistically impossible. No human drill could ever survive the journey hundreds of kilometers down into the mantle. Fortunately, the Earth occasionally sends samples up to us. Deep volcanic activity acts like a high-speed elevator, naturally carrying rare diamonds that formed deep within the mantle straight up toward the surface. Inside one of these deep origin diamonds, scientists found a flaw, a microscopic inclusion of ringwoodite perfectly sealed and preserved. When they analyzed it in a lab, the ringwoodite contained real structural water. This volumetric chart illustrates the true scale of that discovery. Extrapolating that single laboratory proof across the entire mantle transition zone reveals an incredibly vast capacity. It could potentially match or even exceed the total volume of every surface ocean combined. Earth contains an enormous, continuous shell of rock saturated with water running right beneath our feet. This rewrites planetary anatomy as we know it. If there is indeed a massive volume of water buried underground, why doesn't it burst out and flood the continents? Look closely at this cross-section of the Earth's solid crust and mantle. The planet operates as a continuous recycling machine. On the downward half of the cycle, moving tectonic plates at subduction zones slowly drag surface water molecules deep into the high-pressure transition zone, where they get locked away inside minerals. Meanwhile, intense internal heat creates upward convection currents. As mantle rock slowly rises back toward the crust, the extreme pressure drops. The minerals undergo a sudden phase change, releasing those trapped water molecules so they can naturally migrate upward and vent back onto the surface through volcanic systems. The oceans you can sail on and the structural water buried in the mantle are two halves of the exact same system, trading places across hundreds of millions of years. This deep water cycle acts as a long-term buffer. It regulates surface climate, drives global geology, and keeps the biosphere remarkably stable over billions of years. Without this mantle reservoir available to constantly absorb and release water over geological time, Earth likely would have dried out completely or become too highly volatile to sustain complex life. That fact changes how we view the rest of the galaxy. Countless rocky exoplanets that appear perfectly dry on their surface could be secretly holding enormous internal water inventories right now. The future of astrobiology cannot strictly focus on finding liquid oceans that sparkle in the light of an alien sun. We have to look for planets with the exact geological mechanics required to bury their water safely underground. A moment of wonder. Every drop of rain you catch on your tongue, every wave crashing on the beach, is just passing through. Ultimately, it is a temporary liquid phase in a billion-year journey through the deep core of our world.